We all use them, right? Apps, websites, software, the stuff that powers so much of what we do every single day. We kind of just expect them to work, don't we? But have you ever stopped to think, what if they didn't? Like, what if every time you tacked an icon, it crashed? Or every time you tried to submit a form online, it just failed? Not a pretty picture, huh? Today, we're going deep, really deep into the world of evaluating computer programs.
And it's a world that's often hidden, isn't it? I mean, most people probably don't give much thought to how software is actually checked and tested and made to be, reliable and actually do what it's supposed to.
Exactly. So consider this your crash course, no pun intended,
Huh.
in understanding how we ensure that software is actually good quality. And it's not just a one-time check, oh, now. This is a process that starts from the very beginning, like the first lines of code, all the way through to the updates you download, months or even years later.
And we're really fortunate today because the sources we've dug into for this deep dive are incredibly comprehensive. They really give us a look at the whole life cycle of a piece of software, from those early design choices to the ongoing maintenance and all those upgrades that, like you said, can happen years down the line.
Exactly. So we're going to start by really unpacking the different levels of testing a program goes through. What kinds of tests are there? What are they looking for? Then we're going to shift gears a bit and look at what happens when a test fails. Like, how are those results actually analyzed to figure out what went wrong and how to fix it?
And it's not just about automated testing either, right? We'll also be digging into the incredibly important role of feedback, and not just from, test results, but directly from the actual people who are using the software. Plus, we'll touch on something that's often overlooked, but so crucial: documentation. Good documentation can make all the difference.
Absolutely. And finally, we'll wrap things up by discussing how software continues to evolve and improve long after that initial release. It's not a static thing. It's constantly being refined and updated. But let's start at the beginning, shall we? With the fundamental process of testing a program. What exactly does that entail?
Well, testing really it's the foundation of good software. It's how we make sure things actually work the way they're supposed to.
Yeah.
And it's not something you just tack on at the end like an afterthought. It's built right into the process from the start. I mean, as soon as that initial coding is done, testing kicks in.
So are we talking like quality control, like in a factory,
Yeah.
making sure each widget meets the specs?
It's similar in that sense. Yeah, you have this idea of what the software should do, what it's supposed to accomplish, right? So the first aim of testing is to check if it actually delivers on that. Does it meet those agreed upon requirements?
Okay, so that's one side of it, checking that it does what it's supposed to. But what about the actual code itself? Like, is there a way to check if the code is, well written or follows best practices?
That's the second core aim of testing. Yeah. It's about verifying that the code itself, the underlying structure and logic, adheres to the intended technical design. It's kind of like making sure the building is structurally sound, not just that the rooms look pretty.
Got it. So you're not just testing the outcome, but also the process, the how it's built part. Now, is there like one giant testing phase, or are there different stages or levels? I mean, you mentioned different types of tests earlier.
Yeah, you're right. It's not just one big test everything phase. There are different levels, and each one looks at the software from a slightly different angle.
Okay, so walk me through it. Like, what are the main levels of testing a program goes through?
All right, so we typically start with something called unit tests.
Unit tests. What are those focused on?
Unit tests are super granular. They zoom in on really small pieces of code, like a single function or module. It's about isolating and testing those tiny bits in complete isolation.
And who typically does those unit tests? Is it a separate testing team or the developers themselves?
Usually it's the developers who create and run these unit tests. They know the code intimately, and they often use very specific limited data to really pinpoint whether that particular function or module is working as expected.
So if the unit tests pass, does that mean the whole program is good to go?
Not necessarily. I mean, think of it like this. You might have a bunch of perfectly functioning Lego bricks. That's your unit test, right? Each brick works perfectly fine on its own.
Right, but that doesn't mean they'll automatically assemble into the Millennium Falcon.
Exactly. You need to see how those individual pieces work together, and that's where the next level of testing comes in, integration tests.
Okay, so integration tests, they're about, what, making sure the Legos connect properly?
In essence, yeah. Integration tests focus on how those individual units, those functions or modules, interact with each other. Do they communicate effectively? Does data flow between them correctly?
So who handles those integration tests? Is it still the original developers or a separate team?
It can be either, really. Sometimes the original developers will take on integration testing, but often it's handled by a dedicated quality assurance or QA team. These are folks who specialize in finding bugs and making sure the software is robust.
So they're kind of like the software detectives looking for any cracks in the system.
Yeah, that's a great way to put it. And what's interesting about integration testing is that it can sometimes involve what's called white box testing.
White box testing. Okay, now I'm really intrigued. What's that all about?
In white box testing, the testers actually have access to the internal workings of the code. They can see the code itself, the logic, the data structures, everything. It's like having an X-ray vision into the software.
So they're not just testing the inputs and outputs, they're actually looking at the guts of the program.
Precisely. This allows them to test very specific interactions between components to see if the data is being handled correctly, if the logic is sound, and if there are any hidden dependencies that could cause problems.
I can see how that would be really valuable, especially when you're dealing with complex software with lots of interconnected parts. But we're not done with the testing levels yet, are we?
Nope, we've still got two more to go. After integration testing comes system testing.
And system testing, I'm guessing that's where you really look at the whole shebang, the entire software application as a complete unit.
You got it. System testing is about taking a step back and seeing how the entire system behaves when it's all put together. It's about testing the software as it would actually be used in a real-world scenario.
So they're not just testing isolated pieces anymore, they're testing the entire user experience.
Precisely. And unlike integration testing, system testing is usually done using a black box approach.
Black box. Is that the opposite of white box testing?
Exactly. In black box testing, the testers don't have access to the internal code. They're interacting with the software purely through the user interface, just like a regular user would. They're focused on the inputs they provide and the outputs they receive, without knowing how the sausage is made, so to speak.
That makes sense. They're trying to simulate how a real user would experience the software. But isn't there still a chance that even if the system tests pass, the software might not actually meet the needs of the people who are going to use it?
That's a really crucial point, and it leads us to the final level of testing, acceptance testing.
Acceptance testing. So this is where you really put it in front of the actual users and see if it does what they need it to do.
You got it. Acceptance testing is the ultimate test, the one that determines whether the software is actually ready to be released into the wild.
So who's involved in acceptance testing? Is it still the QA team, or are we talking about actual end users at this point?
It can vary, but ideally it involves both the developers, the QA team, and representatives of the actual users, like stakeholders from the client side, or even beta testers who get early access to the software.
And what are they specifically looking for during acceptance testing?
They're essentially verifying that the software meets all the agreed upon requirements, that it functions correctly in a real-world environment, and most importantly, that it actually meets the needs and expectations of the people who will be using it day in and day out.
So it's not just about passing a bunch of technical tests, it's about making sure the software actually solves the problem it was designed to solve.
Precisely. Acceptance testing is about getting that final sign-off, that stamp of approval that says, yes, this software is ready for prime time.
Okay, so we've got these 4 levels of testing: unit, integration, system, and acceptance. Now, where do these actually fit into the whole process of building software? I mean, software development is a pretty complex process in itself, right?
Yeah, it's definitely not just about writing code. There's a whole life cycle to it. And the specific approach to testing can vary depending on which software development model a team is using. Our sources talk about a few different models, like the waterfall model, the V-shaped model, and the agile model.
Okay, so break it down for me. What's the difference between these different software development models, and how does testing fit in?
In the waterfall model, it's kind of like a, well, waterfall. Each phase flows into the next in a linear sequence. You start with requirements gathering, then move to design, then coding, then testing, and finally deployment. So testing basically happens in one big chunk at the end.
So it's like writing a whole book and then handing it to an editor to proofread it all at once.
Exactly. And you can imagine that can lead to a lot of back and forth if the editor finds a bunch of errors early on. It's not the most efficient approach, but it can work for simpler projects.
Okay, what about the V-shaped model? How does testing work in that one?
The V-shaped model is, well, it's shaped like a V. The idea is to have specific testing phases that directly correspond to each development phase. So as you're defining the requirements, you're also planning your acceptance tests. As you're designing the system, you're thinking about your system tests, and so on. It's a much more integrated approach, and it helps to ensure that testing is considered throughout the entire process.
I can see how that would be more efficient. You're catching potential problems earlier on and preventing them from snowballing into bigger issues later. But what about the agile model? That one seems to be really popular these days.
Agile is all about flexibility and iterative development. You break the project down into smaller chunks called sprints, and you focus on delivering working software at the end of each sprint. So instead of having one big testing phase at the end, testing is happening continuously throughout the development process. It's like getting constant feedback as you're building the software, which allows you to adapt and make changes quickly.
So it's kind of like having a mini testing phase at the end of each sprint, making sure that piece of the software is working as intended before you move on to the next one.
Precisely. And this constant feedback loop is incredibly valuable for catching errors early on and ensuring that the software stays on track to meet the evolving needs of the users.
It sounds like Agile would be especially well suited for projects where the requirements might change or evolve over time, right?
Absolutely. It allows for a lot more flexibility and responsiveness to those changing needs. Now, regardless of which development model you're using, the focus of the testing shifts at each level, right? We talked about those different levels: unit, integration, system, and acceptance.
Right. So what are the key things that testers are looking at during each of those levels?
Well, with unit testing, it's all about making sure each individual function or module is working correctly in isolation. You're verifying that it's producing the expected output for a given input, that it's handling data correctly, and that it's not introducing any unexpected side effects.
It's like making sure each ingredient in a recipe is measured correctly before you start mixing everything together.
Exactly. Then, with integration testing, the focus shifts to how those individual units work together. Are they communicating effectively? Is data being passed correctly between them? Are the interfaces between the units well-defined and consistent?
So it's like making sure the different parts of a machine fit together smoothly and that the gears are meshing properly.
Yeah, that's a good analogy. Then with system testing, you're taking a step back and looking at the whole system, as we talked about earlier. You're testing end-to-end scenarios, making sure the software behaves as expected when all the different parts are working together.
So it's like taking the whole machine for a test drive and making sure it can actually perform the tasks it's supposed to.
Precisely. And finally, with acceptance testing, it's all about making sure the software meets the needs of the users, that it's intuitive to use, and that it solves the problem it was designed to solve.
So it's like getting the final seal of approval from the customer, the one who's actually going to be using the machine day in and day out. Now, we also mentioned that there are different types of tests, right? Not just different levels. What are some of the most common types of software tests?
Yeah, so beyond those levels, you have various types of tests, each with its own specific focus. You have functional tests, which are all about verifying that the system does what it's supposed to do, that the features work as expected, and that the inputs produce the correct outputs.
So functional tests are like the basic sanity checks, making sure the software actually functions at a fundamental level.
Exactly. Then you have platform compatibility tests, which are incredibly important these days.
Especially with so many different devices and operating systems and web browsers out there.
Exactly. Platform compatibility tests ensure that the software works correctly across all those different environments. You don't want your app to only work on the latest iPhone, right? You want it to work on older iPhones, on Android devices, maybe even on some tablets.
So you're testing it on a whole bunch of different devices to make sure it's not picky about where it runs.
Precisely. Then you have robustness tests, which are kind of interesting.
Robustness tests, what are those all about?
Robustness tests are about seeing how well the software handles unexpected or even invalid inputs. What happens if a user enters a negative number in a field that's supposed to be positive? Or what if the network connection drops in the middle of the process?
So you're basically trying to break the software to see how gracefully it fails.
In a way, yeah. You want to see if it crashes completely, if it provides a helpful error message, or if it somehow manages to recover and keep going. Robust software should be able to handle those kinds of edge cases without completely falling apart.
That makes sense. You want your software to be resilient, not fragile. What other types of tests are there?
Well, then you have performance tests, which are all about speed and efficiency.
So you're measuring things like how long it takes to load a page or to process a request.
Exactly. You want to make sure the software is responsive, that it doesn't take forever to complete tasks, especially when multiple users are accessing it simultaneously. Performance testing often involves simulating those high-load scenarios to see how the software holds up.
So you're basically stress testing it to see if it can handle the heat.
Precisely. And finally, you have usability tests, which are focused on the user experience.
Usability. So this is where you're really thinking about how easy and enjoyable the software is to use.
Exactly. You want the software to be intuitive, easy to navigate, and visually appealing. Usability testing often involves observing real users interacting with the software, seeing how they navigate, what problems they encounter, and how satisfied they are with the overall experience.
So it's about getting that real-world feedback from actual users to make sure the software is not just functional, but also user-friendly.
Precisely. And all of these different types of tests are crucial for ensuring that the software is high quality, reliable, and ultimately meets the needs of the users.
Now, with all this talk about testing, I'm curious, how much time and effort actually goes into this whole process? I mean, is it just a small part of software development, or is it a pretty significant chunk?
It can vary depending on the complexity of the software, but one of our sources really emphasizes the importance of having dedicated testers, people whose primary focus is to find those potential problems and ensure quality.
So you're saying it's not just something that the developers do on the side, it's a specialized role.
Often, yes. And this source points out that testing can actually consume a pretty significant portion of the overall development timeline, sometimes as much as a quarter of the entire project.
Wow, a quarter of the project. That really underscores how crucial testing is to the success of a software project.
Absolutely. And it's not just about the time it takes to run the tests themselves. It's also about the time it takes to analyze the results, to fix the bugs, and to retest the software to make sure those fixes actually work.
It's a pretty involved process. Now, is there anything else that's particularly noteworthy about this whole testing process?
Yeah. One thing that our source mentions is the importance of using what's called a testing version of the software.
The testing version, what's that exactly?
It's basically a specific build or snapshot of the software at a particular point in the testing process. It's like a frozen version that testers can work with, knowing that it's stable and that it represents a specific point in the development cycle.
So it's kind of like a reference point, a way to ensure that everyone's testing the same thing and that the results are consistent.
Exactly. It also allows developers to track which version was tested, what the results were, and to revert back to a known good state if they discover major issues during testing.
That makes a lot of sense. It's like having a safety net, a way to roll back to a previous version if things go wrong. Anything else that stands out?
One interesting point that our source brings up is the idea that the Pareto principle often applies to software testing.
The Pareto principle,
Yeah.
that's the 80-20 rule, right?
Yes.
Like 80% of the effects come from 20% of the causes.
Yeah, exactly. And in software, it often turns out that a small percentage of the code base, maybe 20%, is responsible for a large majority of the problems, maybe 80%. So by focusing their efforts on those high-risk areas, testers can significantly improve their efficiency and find more bugs with less effort.
That's a really fascinating insight. So it's not just about testing everything equally, it's about being strategic and focusing on the areas where you're most likely to find problems. Okay, so we've covered testing the program as a whole, but what about testing those building blocks of software, like data structures and algorithms?
That's a crucial point. Our source really stresses that testing these fundamental elements isn't optional. It's absolutely essential for making sure that the entire system is built on a solid foundation.
So we're talking about things like lists, arrays, trees, those kinds of data structures.
Exactly. And thoroughly testing those data structures provides invaluable feedback about the quality of the code, allowing developers to identify and resolve issues at a very fundamental level.
So it's like making sure the bricks you're using to build your house are strong and durable before you start laying them down.
Precisely. And when you catch errors early on in those core components, it prevents them from cascading into more complex problems later in the development cycle.
Right, because if you're building a house on a shaky foundation, the whole thing could come crumbling down.
Exactly. And beyond just preventing major problems down the line, data structure testing also helps to boost the team's effectiveness overall. When everyone is confident that the core components are working correctly, it frees them up to focus on more complex aspects of the software.
It's like knowing that the plumbing and electrical wiring in your house are solid, so you can focus on decorating the rooms and making it look nice.
Exactly. Now, when it comes to actually evaluating how well you're testing your data structures, our source highlights some interesting hypotheses from MIT scholars.
Oh, this sounds intriguing. What are those hypotheses all about?
The first one is called mutation, and it's based on the idea that you can gauge the effectiveness of your tests by introducing small, deliberate errors into the code.
So you're intentionally creating bugs to see if your tests can catch them.
Exactly. These intentional errors are called mutants, and if your tests are robust, they should be able to detect those mutants and flag them as problems.
So it's like setting up a trap for the bugs to see if your tests are sharp enough to catch them.
Exactly. Then there's the coverage hypothesis, which focuses on the idea that the quality of your test suite isn't just about how much of the code it covers.
So it's not just about hitting every line of code with a test.
Right. It's about making sure that your tests are designed to be effective across multiple, slightly different versions of the program. So a test that works well on version 1.0 of your software should ideally also work well on version 1.1 and version 1.2, even if there have been some changes to the code in between.
So it's about making sure your tests are adaptable and resilient to change.
Exactly. Then you have the feasibility hypothesis, which is all about whether your testing approach can actually provide meaningful results for your specific goals.
So it's about making sure you're using the right tools for the job, that your tests are actually designed to answer the questions you're asking.
Precisely. And finally, there's the randomness hypothesis, which suggests that for data structure testing, a more exhaustive approach, trying a wide range of different scenarios and input combinations, is generally more effective than just randomly selecting a subset of tests to perform.
So it's about being thorough and systematic in your testing, not just hoping that you'll randomly stumble upon the bugs.
Exactly. Now, beyond those high-level hypotheses, our source also points out some specific aspects of the data structures themselves that testing should focus on.
Okay, so what are some of the key things to look at when testing data structures?
Well, first and foremost, you want to make sure that the naming conventions used for the data structures are clear and consistent. If you have a data structure called customer list, it should actually be a list of customers, not a list of products or something else entirely.
Right, you want the names to accurately reflect what the data structure actually contains.
Yeah.
What else?
You also want to make sure that the data types used for the data being stored are appropriate. If you're storing a customer's age, it should be an integer, not a string. And if you're storing their name, it should be a string, not a floating point number.
Right, you want to use the right data type for the job to avoid any potential errors or misinterpretations.
Mhm.
Anything else?
You also want to check the actual values held within the variables and data structures to make sure they're correct and consistent. If a customer's age is supposed to be between 18 and 100, you want to make sure that there are no customers with ages of 0 or 200.
So you're looking for any data that's out of bounds or doesn't make sense in the context of the program.
Precisely. And you also want to check the accuracy of any computations performed on that data. If you're calculating the average age of your customers, you want to make sure that the calculation is correct and that you're not accidentally dividing by 0 or something like that.
So it's not just about the data itself, it's also about how that data is being manipulated and used within the program.
Exactly. And ultimately, all of this testing is about ensuring the overall integrity and accuracy of the calculated results. You want to be confident that the data you're working with is reliable and that the program is producing meaningful outputs.
Okay, so we've covered testing programs generally, and we've looked at data structures specifically. Now, what about algorithms? How do those fit into the picture?
Algorithms are the heart of software, really. They're the step-by-step procedures that solve specific problems, and it's absolutely essential to test whether they're doing their job correctly and efficiently.
So an algorithm is like a recipe for solving a particular computational problem.
That's a great way to put it. And just like with a recipe, you want to make sure that the steps are clear, that they're in the right order, and that they actually produce the desired outcome.
So what's the typical process a developer goes through when they need to test an algorithm?
Well, first and foremost, they need to have a really thorough understanding of the code itself, how the algorithm has been implemented in a specific programming language.
So they need to know the recipe inside and out before they can start testing it.
Exactly. Then they need to define one or more test cases. These are specific scenarios with known inputs and their corresponding expected outputs.
So it's like saying, if I put these ingredients into the recipe, I should get this specific dish as the output.
Precisely. Then they need to set up a test environment, a place where they can reliably run the algorithm and observe its behavior.
So it's like having a dedicated kitchen where you can test out your recipes without any distractions.
Exactly. Then they'll input those specific test values into the algorithm and see what happens.
So it's like actually following the steps of the recipe and seeing if you get the dish you're expecting.
Precisely. And finally, they'll carefully assess the algorithm's execution and compare the actual results it produces with the predetermined expected outcomes.
So it's like tasting the dish you made and comparing it to what you were hoping to achieve.
Yeah.
Now, are there different ways to actually test algorithms? I mean, you talked about defining test cases and running the algorithm, but are there different techniques or approaches?
Absolutely. One fundamental method is called desk checking.
Desk checking, what's that all about?
Desk checking is a very manual process, but it can be incredibly valuable for understanding how an algorithm works. Basically, the developer takes on the role of the computer and manually walks through each step of the algorithm.
So they're pretending to be the computer, executing the code line by line.
Exactly. And as they go through each step, they keep track of the values of all the variables involved in the algorithm. They might use a table or a spreadsheet to organize this information.
So it's like creating a little logbook to keep track of what's happening inside the algorithm as it's being executed.
Precisely. And by carefully tracking the values of the variables at each step, the developer can identify any logical errors or inconsistencies in the algorithm.
So it's a way to really get under the hood of the algorithm and understand how it's working at a very granular level.
Exactly. And then there's peer checking, which is another valuable technique.
Peer checking. So you're getting a second pair of eyes to look over your algorithm.
Exactly. Peer checking involves having a colleague, another developer on the team, review and test your algorithm.
And what's the benefit of that?
Well, for one thing, it helps to overcome any biases that the original developer might have. If you've been working on the same piece of code for a while, you might start to miss certain things or make assumptions that aren't necessarily true.
It's like when you're proofreading your own writing. You often miss your own mistakes because you're so familiar with the text.
Exactly. So having someone else look at your code with a fresh perspective can help to catch errors that you might have overlooked. Plus, different developers often have different approaches and ways of thinking, so they might spot potential problems or edge cases that you hadn't even considered.
It's like having a second chef taste your dish and give you feedback.
Mm.
They might pick up on subtle flavors or textures that you hadn't noticed.
Precisely. And then there's another technique called a walkthrough.
A walkthrough. So you're literally walking through the code line by line.
In essence, yes. A walkthrough is a more structured approach to code review, where the developer who wrote the code explains each line to a group of other developers, usually including the testing team.
So it's like a presentation where the developer is explaining their code to an audience.
Exactly. And the purpose of a walkthrough is to identify any potential logical flaws, misunderstandings, or ambiguities in the code. The other developers can ask questions, point out potential problems, or suggest alternative approaches.
So it's a collaborative process where everyone is working together to ensure the quality of the code.
Precisely. Now, the complexity of algorithm testing can vary quite a bit depending on the algorithm itself, right? Some algorithms are relatively simple, while others can be incredibly intricate and difficult to test thoroughly.
So how do you approach testing a really complex algorithm?
Well, for more complex algorithms, the testing process can become quite involved. It might require specialized testing systems, specific hardware and software configurations, and the development of very detailed test procedures.
So it's not something you can just do on your own computer with a simple text editor.
Right. You might need access to specialized testing tools, simulators, or even custom-built hardware to accurately test the algorithm in a realistic environment. And you might need to create a large and diverse set of test data to cover all the potential scenarios and edge cases.
So it can be a pretty demanding undertaking.
Absolutely. And in some cases, you might even need to develop what are called reference algorithms to compare against. These are well-tested, highly reliable implementations of the same algorithm, often written by experts in the field.
So you're basically using a gold standard to measure the accuracy and efficiency of your own algorithm.
Exactly. And then, of course, there's the process of rigorously documenting the entire testing process, including the test cases, the test data, the results, and any conclusions or recommendations.
So testing complex algorithms is a pretty involved process, but it's essential for making sure that the software is reliable and performs as expected. Now, we've talked about actually performing the tests, but what about analyzing the results of those tests? I mean, what happens after you've run a bunch of tests and you have a bunch of data?
Analyzing the results of testing is just as crucial as performing the tests themselves. It's where you really start to gain insights into the quality of the software and identify areas where improvements need to be made.
So it's like a detective examining the clues to solve a mystery.
Exactly. And just like a detective needs to organize their evidence, testers need to organize and analyze the data they've collected from their tests. And one of the key ways they do that is through test reports.
So test reports are kind of like the detective's case file, where they document their findings and their conclusions.
Precisely. And there isn't just one generic test report. Our source highlights a whole range of different types of reports that might be generated throughout the testing process.
Oh, wow. So what are some of those different types of test reports?
Well, at the highest level, you have what's called a master test plan, or MTP.
Master test plan. So that's like the big picture overview of the entire testing strategy.
Exactly. It outlines the scope of the testing effort, the objectives, the resources, the schedule, and the overall approach to testing.
So it's kind of like the blueprint for the testing process.
Precisely. Then you have level test plans, or LTPs, which are more specific plans for each level of testing.
So you might have an LTP for unit testing, an LTP for integration testing, and so on.
Exactly. And these LTPs would detail the specific tests that will be performed at each level, the data that will be used, the expected outcomes, and the criteria for passing or failing the tests.
So they're like the detailed instructions for each stage of the testing process. What other kinds of reports are there?
Well, then you have level test cases, or LTCs, which document the individual tests that are being performed.
So each LTC would describe a specific test, like test that the login button works correctly, or test that the shopping cart calculates.